Okay, so in this video, we'll be solving an exercise about language operations. So we essentially want to know what the result of these language operations are when we have these two languages. So the first one is language union. Language union is just like a set union. So if I have L1 is A, A, B, A, B, A, B, and I have L2, which is AB power n, where n is a natural number. Then AB power n is AB square, AB cube, and so on. And so you'll notice that this is AB square, and there's sort of also AB1 here. So that means that when we take the union, we have L1 union L2, then we take everything from L1 and everything from L2 and we put it all together. So we'll have AB square from L1, and then AB square, AB cube, and so on from L2, because sets do not allow for for duplicates. We'll just remove the duplicated instances of AB and AB square. And so really actually what we get is we get that L1 L2 is the singleton language, which contains A union L2. Okay, then what about the intersection? Well, the intersection, we've already kind of noticed what the intersection is. It's AB and AB squared, right? Those are the two strings that are common between L1 and L2. So L1 intersect L2, that's going to be all of the strings that are both in L1 and L2. Because L1 is the shorter one, I can just say, well, is A and L2, whoopsies, is A and L2 no? Is AB yes? Is AB squared yes? So then I just get AB and AB squared. Okay, the third question is, whoopsies, what is L1 different L2? So L1 different L2, that's um, everything that's in L1 but not in L2. So the way that you can do this, maybe a bit mechanically, is um, you go through each element in L1, you check if it's in L2. If yes, you remove it. If not, you keep it, right? So is A in L2? No, so I keep it. What about AB? It is in L2, so I remove it. What about AB squared? It also is in L2, so I'll remove it. Okay, and then the last one is just doing L1 different L2, L2 different L1, sorry. Instead of redoing the same manipulation, I'll just note that, actually, is this going to help? I was going to note that this is L1, this is L2 intersect L1 complement. Um, yeah, that doesn't really help in sort of easing the computation, but this is just a property to remember. So just be aware of this property. In this case, this doesn't really help me in computing L1 different L2, L2 different L1, because L1 complement is, sigma star except for AB, and AB squared. So, I mean, doing the intersection, it doesn't really help all that much, I find. So instead, I'm just going to repeat the same manual process. In this case, I can't go through each element in L2 because it's infinite. So I'm just going to notice if there are any patterns. So for L2, I have strings that look like AB power n. Do I have any strings that have the same pattern in L1? Well, yes, I have two, right? I have AB, whoopsies, I have AB and AB squared. So that means that L1 different, I keep saying the opposite. L2 different L1, there we go, is AB power n, except for the first two uh, natural numbers. So it essentially starts at AB power cube and AB power 4 and so on. And so I can write this a bit more compactly as AB power n, where n starts at 3 and n is an integer. Okay, so that solves the first question, or this exercise on language operations.